Can you see the slide? I'll take that as a yes.
Yep.
So today I'm going to talk to you to conclude this workshop. I'm going to take the kind of opposite approach than SMAC, so you'll be able to compare the advantages and drawbacks. Because I'm going to talk to you about hacspec, which is a succinct, executable, verifiable specification language for high assurance cryptography embedded in Rust. We've had quite a bit of a rebranding because the website was called Rocks, but we changed the name to hacspec and we're going to stick to hacspec. So that's how you'll be finding it on the internet. This is joint work with my PhD advisor, Karthikeyan Bhargavan, and Franziskus Kiefer from Wire, the messaging app company. And I'll begin this presentation by the story of how we came to design hacspec, which is kind of a tale of two worlds, because it's going to be the world of Rust on one side and the world of cryptography on another side. And we'll start by the observation that Rust is memory safe, well, with all the asterisks with unsafe code, etc. And that's prompted cryptographers to select it as a language of choice to write high assurance cryptography, because most of the bugs related to cryptography and security are related to memory safety. So choosing Rust, as you all know, is a way to circumvent that. Hence, there's a new shiny Rust band for cryptography libraries with names such as Trust Crypto, Data Cryptography, Ring, RustPQ for post-quantum cryptography, but also whole protocols written in Rust, such as RustTLS. And this new band has kind of distance from the old verified guard of cryptography, verified cryptography libraries, with projects such as Evercrypt, Hacklestar, Veil, which are all like bundled with the same thing, but also Fiat Crypto from the MIT or Jasmine Crypt from the École Polytechnique and other institutions. And there's kind of a growing distance between those two worlds, and the point of hacspec is to reconcile those two worlds, and so that cryptographers can write their applications in Rust, but also enjoy the guarantees brought by verified implementations. And there are several ways to go about that. The first and simplest one is to simply provide bindings in Rust from verified implementations that already exist. And this is the case with one Evercrypt crate, but you can also have Jasmine Crypt bindings or Fiat Crypto bindings in Rust. It poses no problem, but we want to go a little bit further than that because we want actually to verify a crypto implementation in Rust. Because not only you need crypto primitives, but you want to build on those primitives to build constructs and then protocols and larger and larger high assurance applications. And as you have been able to see in this workshop, the verification tools are still maturing. Hopefully one day they will handle the full functional correctness proof for crypto libraries with like 10,000 or 100,000 lines of code. But it's still not there, so we have to find something in the meantime. And our approach is rather focused on crypto, and we do not aim to become like a general purpose verification tool for Rust. But we found that there's an Achilles heel in verified implementations. And this Achilles heel is the specifications. Indeed, verified implementations usually prove functional correctness, but functional correctness has to be proven with respect to something. And this something is a specification that has to be written in the specification language of the proof assistant. And usually it's written by students and the source from those specifications are like some pseudocode written in some RFC or some informal description of how the crypto primitive should work. And this is, of course, informal specs lead to specification bugs, which render completely useless all attempts to verify implementations. So we want our specs to be right. And there has been an attempt to convert, to get cryptographers to write their specs in at least a programming language that executes with Python a few years ago, but it had little traction. Maybe because of Python, we don't know. But we're coming again to an attempt at having formal executable specifications that cryptographers can write in order to fix that Achilles heel of verified implementations. And the idea is that since cryptographic code is DSL friendly, it doesn't exercise like all the corner cases of undefined behavior and other cryptic language features. So we're going to make an embedded DSL for Rust for cryptography. And the objectives are twofold. For cryptographers, we want to offer them convenient tooling to write executable specifications and or reference implementations for their cryptographic primitives or protocols or even larger apps. Of course, those won't be performance oriented, but so we also want for them to be easily, to have the possibility to easily switch to a native Rust, like unsafe heavy optimized implementation. And for proof people, well, this language is aimed at providing the proof people with a steady source of correct, reviewed by domain experts specifications that they can then take as a basis for their functional correctness proofs, therefore reducing the trusted computing base for proof development. Without further ado, let me present you a taste of what hacspec looks like. Well, it's an embedded DSL, so it looks like Rust. And as you can see, the first thing that strikes your mind is that there's no borrowing. Indeed, since we wanted this DSL to have simple semantics, which means that we had to take radical decisions in order to cut whole branches of complex Rust semantics, which we didn't want to talk about. And the actual trade-off that we had while designing this language is on the one hand, that cryptographers should be able to write beautiful specs, like succinct and that don't look ugly. And on the other hand, we don't want too much features in the language in order to avoid the semantics creep, which will lead to very complex formalizations. And I know some people in the audience have yet dealt with all those semantics complications in Rust, and we didn't want to go through that. We leave that to experts. And for more complicated functions like this main poly loop, you can see that it's all about like for calling functions with some kind of sequences. So we have like slicing, we have for loops that are indexed by integers, and it's generally a feeling of Rust. We have also mutable variables, which are then translated to some kind of state monad with that keep like the variables as the state of the variable as the state. And you can see that we allow a little bit of borrowing, but in very particular places. It's only at the top level, only in function arguments. And this is like really focused so that we have several few semantics rules to deal with that, but it doesn't overcreep into the rest of the language. And this is purely like a syntactic criteria to determine like where you're allowed to put the borrowings. And of course, no mutable borrowing, and functions can't return references. So this DSL, which is radically simple and we wanted it to be, is formalized. So we have a syntax. You can see that it's a list of functions, but also we have type declarations to declare certain types as fixed length array. We have two kind of fixed length array, one which is like whose length is known at compile time, and the other whose length is not known at compile time. This distinction is useful because with the first kind, you can implement the copy type, which is very useful to have specs look nice, to not insert clone everywhere. You can see that we make a strong distinction between types that don't contain references inside them, and the reference is only allowed at the top level on certain types with the tau mu distinction. Concerning statements, we have fairly limited, it's only let bindings, conditional for loops, and also array updates and array indexing. And concerning the expression, we're fairly straightforward. We have tuples. We currently don't have structs and enums, though we're planning to add them in the future. And we have also array indexing and all of the usual operator on integers. We provide this language with a simple call by value semantics with context that's just the variables, the local variables of a function. So values are like usual values plus arrays and tuples. And the shape of our judgments is really simple. We just have this variable context and the expression or function argument or statement evaluates to a certain value while changing the variable context. All the rules for semantics are presented in the paper. You should go and read the technical reports if you want to get more precision about that. We also provide typing judgments that is meant to respect Rust specificities with linear typing. So we have a typing context containing both tuple functions and variables. We have a type dictionary to provide the indirection and the nominal nature of Rust struct typing. And we have a linear context splitting to implement the linear nature of Rust type system, which with an escape hatch, which is the implementation of the copy traits. We don't implement traits, we don't formalize traits in our language. We take it as some types do implement them and some other don't. It's part of the context. And we have simple typing judgments. The rules are a little bit tricky because we have to kind of provide manual cases for each times where you're allowed to borrow. But since we keep borrowing to a very reduced number of places, the rules are manageable, and you can see the full formalization in the paper. So then, because we want to offer convenient tooling to cryptographers, we had to implement a type checker and basically compiler for this embedded DSL. And of course, we do that as a plugin to the Rust compiler. But then, we took an unusual choice with respect to the other tools presented in the workshop, because we wanted our representation to be very, very close to the source code. And as you know, Mir is very desugared and is in basic blocks form. So I know there are workaround around. You can work around that by like restructuring the control flow. But we really wanted to have something that's very close to the source code because we want to translate to other verification tools. We want the specs translated to look almost as the same as the original source code. Hence, at the expense of having to re-implement some of the things that are done between AST and Mir, like traits and method resolution, or the borrow checking, which you have to read on by hand, which shows the AST as our source intermediate representation within the hacspec compiler. And so let me show you a little architecture diagram of the hacspec type checker. So it's implemented as a, why not use HIR? This is a good question because HIR has a little bit of syntactic sugar, and we didn't want to deal with that, especially with respect to for loops. It desugars the for loop into a while loop, I think, and it was not convenient for our users. So we took AST, also because it allows us to control more easily with respect to what we get in the source code. So here's a little architecture diagram of the usual Rust C pipeline, AST to HIR to Mir with type checking, borrow checking, external crates. And hacspec fits right here. We take the Rust AST, we translate it into a hacspec AST by in the process rejecting all the programs that are outside the bounds of the DSL. And then we perform the hacspec type checking. And we also have support for external crates, meaning that you can split your programs in several crates, and we integrated compiler architecture that lets you split your hacspec programs into several crates, which is something that is quite painful in terms of engineering, but which we thought was crucial. Here's a list of hacspec programs that we are already written and already type checked with respect to the DSL. They're all crypto primitives for the moment, although we're working on some more ambitious programs, such as a implementation of the TLS13 client, which is about like a 1,500 lines of code. So we put the Hacklestar column as a comparison to show you that the specs that we write in hacspec are very succinct and as or more succinct as the specs that are traditionally used inside the proof assistance to serve as a basis of functional correctness. And this was very important because we want the specs to be succinct and as small as possible because they're the trusted computed base. So we want them to minimize that. And here is what the outputs in a verification backend looks like. And you can see that the cha-cha-line function, which I was showing to you earlier, all the arguments have been desugared into like F-star arguments. Here we put a little bit of a type refinement that we had to put manually in order for it to type check. In future work, we want to use some of the specification require essential language that has been developed by somebody else to be able to generate those kind of type refinements automatically from the source code. And the array updates are just simply desugared into functional updates to the same variable. And we have a little bit of name resolution pass to ensure that everything is running smoothly. But the output of our toolchain is relatively similar to the original code. And we want that because then proof people are going to look at that code to prove functional correctness against implementations. So succinctness and pleasantness to read is definitely something that we look for. On top of the language, we have several libraries that provide convenient functions that cryptographers always use in their implementations. We have a crate for secret integers that are just wrappers around signed and unsigned integers, but that forbid all non-constant time operations. You can also use that crate separately from the hacspec language, actually. We have a crate for abstract integers that are verification-friendly bounded natural integers. And because they're bounded, we can fit them inside an array of U8s that implements the copy traits. So when you use them, you don't have to write clone everywhere because it implements the copy traits. We use little schemes like that to really improve the succinctness of the specs. It's adapted for field arithmetic-based specification, which is a big thing in crypto. And lastly, we have the standard library of hacspec, which you are required to import whenever you want to use the hacspec DSL, because some of the objects in that library have a hard-coded translation to some of the libraries in the verification backend, which is, so the hacspec library is also part of the trusted computing base in some sense. We have a copyable constant length array with array, the array macro, linear fixed length array with sec, and we have traits and helper for the specification writers that are integrated with the typechecker with a whitelist system. In conclusion, this is an ongoing research collaboration between formal methods people, mostly represented by INRIA with my PhD advisor, Karthik, and me, but also with many cryptographers, the first of whom being Franziskus, Kiefer at Wire, but we also are talking with various professors that are leading verified crypto implementations research teams all over the world. Some of them already put students of theirs to write a specification in hacspec, so the community is kind of growing. The objective of the project is to bridge Rust cryptography with existing verification tools for crypto. And the philosophy is to capture in this DSL the functional part of Rust, because actually when you write crypto specifications, you only care about you only need a functional language actually, and we want to keep the mutable parts and the mutable states to a minimum, because when you are doing verified implementation, you really want to keep in your trusted computing base the mutable references and mutable aspect of your specifications to as low as possible. So there's a website whose link is on the screen. The code is, of course, available online, both the code for the hacspec programs written so far and the code of the compiler in typechecker. And there is a technical report so you can refer to if you want more details on the formalization and on any of this. Thank you for your attention, and I think I finished a little bit earlier, but as this is the end of a long workshop, this might be also good for everyone.
Thanks for that talk, Denis. We do have time for a few questions. So Yannick has a question. Yannick, do you just want to ask a question?
Yeah, sure. Oh, you can read it.
Yes, thanks, Yannick. So crypto it's kind of the same family of languages. I don't have the precise comparison of what in terms of what features are missing in hacspec and what features are in Cryptol. So yes, for the recording, the question is, how do you compare hacspec with Cryptol? Do you gain in expressivity, for instance, compared to the fixed size of data in Cryptol? So my understanding is that Cryptol is heavily skewed toward spitting out assembly, isn't it? Hence, yes, which is why you have fixed size of data. So hacspec is a little bit expressive because it's mostly aimed at spitting out OCaml, let's say ML. So and then it's used through verified implementations that are in C. So there's a little bit more flexibility in terms of expressivity. So for instance, our sec, you can pass an arbitrary sized buffer as an input to your encryption function, for instance.
I could say a little bit more about the comparison with Cryptol if folks would be interested in that. So I think the biggest difference between them is just the structure. Cryptol is a purely functional language and uses sort of functional idioms for describing programs, whereas a hacspec, even though it is copying things around, uses Rust and is kind of more imperatively structured and probably more familiar to a lot of programmers. So Cryptol does track sizes very precisely, but does allow you to write things that are sort of polymorphic over sizes. But it does mean that you are kind of constricted when you're writing a program to be sure that all of your functions correctly preserve the sizes that are described in the types. So a big part of it is that it's got a type system that tracks the size of everything. And so it is fixed for any particular run of the program, but not necessarily for the definition of a particular function.
Well, okay, thanks for the precision. So Ralph asks what the next step is, wiring up some automated prover for Rust code with hacspec as a spec language. Well, it's one of the next steps involved. So I started this project with the goal of doing some Rust verification in the spirit of Prousty or Crusoe or other projects. And then I got sidetracked, mainly because doing Rust verification is really difficult. And the goal of this project, which is Prosecco's goal, is to link up cryptography and formal methods. So I ended up with a different direction. But I would say that since hacspec has a formalization and we know precisely what are the bounds of the language, then I think you can take those hacspec programs and wire them up, as you say, with other existing provers, maybe Prousty, maybe Crusoe, maybe even translate to Rust Belt for verification, to serve as a basis for, let's say, a fiat crypto specification. I think the doors are open at that stage, but I think it's still future work. There's a question from Yusuke. Do you have a plan about supporting mutable references? I believe that you can use Rust horns reduction for that. Indeed, I followed the Rust horn and the prophecy variable inspiration with close attention, and this is a very good thing because it enables you to kind of take those mutable references and translate them into a purely functional word. So we could strive too hard to have an F-star encoding of those prophecy variables, maybe with some kind of layered effect, because F-star has a powerful effect system. It's in the realm of possibilities, but we currently don't have, it's not in our critical path, since we want to really extend the kind of hacspec programs that we want to write to extend that to protocols, for instance, as we're writing this TLS client. So right now I'm mostly adding a few features to the hacspec language, which are a little bit disruptive, but not too much. One is the ability to have early return in your functions, because when you write protocols, you always put question marks at the end of your statements, and we don't want cryptographers to relinquish that really good styling with some like if then else, and so we want that, and we want to support like structs and enums, because when you write some meaningful programs, these are really important. But Yeah, I think it's possible, and I think it's the path I would choose to extend that the hacspec spirit to mutable referencing. I hope I've answered the two questions.
Yep. Are there any other questions? Okay, well, great. Well, thanks for the talk, Denis. So that brings an end to the workshop.